Hey guys, and welcome to the video. In this session I want to cover generator expressions, and more specifically I want to compare these to list comprehensions and effectively argue the case as to why I think these are better in some cases and when you should use them. So what I want to do is set up a quick list comprehension here, and let's just do I for, let's do I for I in range, let's just do from 1 to 11 here. Okay, there we go. So let's print this off and see what's going on. So you might be familiar with list comprehensions. Let's hit run. There we go. So this is simply saying I for I in range of this here. Now, normally in list comprehension, what we're doing is we're having some iterable. In this case, we're going over each item in the range of 1 up until 11. So in this case, stopping at 11, so therefore we get 10. We want to do some action here, so something at the front. Now, the problem with list comprehensions is that it does all of this computation basically on this line before it then moves to the line below, which is okay. I mean, for some cases like this is completely fine because we're only asking for 10 items. However, what happens when we ask for a large number of items, perhaps going through a more expensive function? We can kind of mock that here. So let's just do some func of x here, and then we'll do return x to the power of x here. Okay, and then what we then want to do with this front I, we'll pass in some func of I like this instead and hit run. Okay, so at the moment this is okay because these are still fairly small numbers. But what we could do, I wonder if we could make this run a whole lot slower. What if we do 1,000 to 10,000? Now this on my machine seems to hit a threshold when it gets really slow. Yeah, there we go. To see how that's just running now. I have no idea how long this is going to take. Okay, maybe like 2 or 3 seconds. I don't know. But yeah, that was definitely a couple of seconds, right? We hit run, and that's still waiting to go. What we can do, just kind of further prove that this is kind of slowing us down, if we print pre and then post here. So we should see pre, that's doing this computation here, and then take your time. There we go, today. Right, okay, for pre and post, what we saw that it took, 3 or 4 seconds or whatever in between. Now, with a list comprehension, I'm going to do it in block capitals. This is doing it all at once. Doing it all at once, there we go. Sorry, it's been a fairly long day today. There we go. Doing it all at once. Now, in a situation where this is taking, like less than half a second or whatever, or you're in a program where you're not entirely fussed as to how long a computation takes, then that's okay. This video might not be for you. However, if you're kind of in the market for making stuff quicker, making things kind of more efficient, then there's actually a really cool and really neat tool we can use to basically say, don't do all this computation now, just do it as I request some of the items from it. And a good kind of use case for this, imagine we just wanted, let's see, let's do lcomp colon up until 3. So we ask for the first couple of items from this. So we'll get pre, should get post in just a second. Come on, there you go. Oh goodness. So there we go. Some pretty sizable numbers, but yeah, there we go. No wonder that took so long. Yeah, so a situation like this where we're creating a structure with lots of things inside it, but we're using the bits kind of one by one or piece by piece. This is when we can use something called a generator, specifically a generator expression. The magic of this is that the items are actually computed when they're asked for, not all at once. So just to come back to this here, this is computing all of these and storing all of them in memory. So, if this was some kind of, I don't know, if you're computing opening text files or making web requests, you can end up with some pretty sizable stuff in memory. Especially if you're not using it all at once, it's kind of a waste of memory. So what we can do, this is where things get really cool, I'm actually going to change this to lcomp to gencomp, get rid of this, and now to switch it, this is the tricky bit, I'm joking, it's not, it's the easy bit, get rid of these square brackets, put in your rounded parentheses, and that's it. This is now officially a generator comprehension or generator expression, and notice the difference there. We hit run, pre-post happens immediately. So why is that? What happened there? You can see what happens if we actually go and print off gen comp here. We don't actually get really anything much back, to be honest. We get this generator object gen expression. If we run dir on this, short for directory, we're going to look at all of the methods and attributes of this generator expression. And there's some that I'm actually really interested in, specifically this guy. Next here, I'm going to take that. And where's the other gun? The other good one? There it is, iter. Now what does this mean? This means, so that basically we can call this next function on it. And this means we can do, we have iter, means we can iterate over it. It means we could do like for I in my object, right? Which is pretty cool. So the one I want to kind of show first is this next here, which basically means give me a single item from this, or in this case, yield me an item from this. And to use next is actually really simple. If I did print next of gencomp here, let's see, and get rid of this. This is basically saying, give me one. That's it, right? So imagine this has, in this case, 1,000 up until 10,000. It's going to have, oh, what's that? 8,000 or so, like 9. Yeah, it's quite. It's too late for maths. It's going to have all these things in memory that I just held there, and they're stored, ready to go, but they haven't been passed into this function yet. They're kind of just there and waiting. However, when you call next, you're basically saying, yeah, I'm ready, give me one now. So if I hit clear and run, there's the first. What you then can do, just kind of further prove this. In fact, let's do it in a for loop. That's probably a lot nicer. So we do for I in range, let's see. In fact, that's quite naughty. You shouldn't use I here. Use the underscore instead. Do for blank in range 3. The reason I'm not using I is because I'm not using I in the loop. And if I did print next of gencomp like this, and oh, no, not like that. So if I scroll all the way to the top, there we go. Nice. So that was our first number, our second number, and our third number here. So basically what this will do, this generator will keep on, as long as if you keep calling next, as long as you haven't exhausted all the items from the generator, it's going to keep on basically producing them. So calling this function one by one of each of these things and spitting them out. I do want to show you what happens if you run to the end. So if I say I did 1, 2, 4, let's just try that. So I get it to go to the end, and then we'll make it fail. So we hit run. Yeah, see we got 1, 4, 27. Let's remove some of these here. So let's try I in range 4. We got this stop iteration. That basically means that, well, it's this saying I've given you all I've got. I don't have anything else left, right? So this has 1, 2, 3 inside it. So we would have done 1 squared, 2 squared, 3 squared. So 3 squared gave us this here. And of course, because this ran an additional time, we called next on an empty generator. And this is like, I have nothing left. Can try and catch it if you want. You can do, you can do this here. And the specific thing you're looking for is this guy, the exact stop iteration here. I don't know, you could just print stop like that and that would work. Here we go. Now the question is, of course this is a video trying to be about efficient Python. Question is, when do you use this? So that's kind of the key thing here. And for me personally, I kind of think the following rules apply. So you basically use it, in my view, the most important one is, if not all items are required at once. I think that's the key there. If if you're storing a big thing in memory and maybe using a few bits, then a few bits later on, a generator is perfect because you can create a generator, you can use next to ask for 3 or 4 things, do some other stuff, define some classes, make some variables, and then you can call next again later on. The generator will basically recall where you're up to in terms of how many things have been taken out, so you can then just resume and carry on. That's fine. And then the last one here, and I think this is also super important, heavy computations. I think that's very important here. Of course, this could be anything like a web request, could be like opening a file, could be some kind of figuring out if a number is prime, which for a big number is quite hard to do. Well, not hard, but it's computationally quite expensive to do. And last one, let me show you kind of a more specific example. Let me get rid of all this for a second. I think this one's actually kind of cool. If you're using all or using any. So let me quickly show you something. So say I did S. Let's just do evens here. 2, 4, 6, 8, 10, right? So this is, I guess, kind of a bit more of a bizarre example, but bear with me. Now, imagine you wanted to write some kind of list comprehension to figure out if these are all even, right? So what we could do, let's just do a new structure, a new array called isEven. So what we could do I mod 2 is equal to 0 for I in evens, right? So think what this is going to do. It's going to say something when divided by 2 has no remainder, right? So if you divide it by 2, well, if you do mod 2, you know, say if you did 10 divided by 2, you got 2, 4, 6, 8, 10, remainder is 0, so that'll basically become 0. So 0 is equal to 0 for I in evens. Now if you did print is even here, true, 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 true. Now what you can do, and this is kind of an interesting thing, if I pass all around this here, what this will do, this basically looks at all of the things inside this list and says if they are all true, the all function will return true. So let's run. And we get true. That's okay. That's cool. Now let's just throw something in strange. Let's just call this nums, right? And then change evens here to nums. Let's do something. Let's do 6. I suppose for some bizarre reason, someone's going to put 7 here. Some troublemaker. And we get false because, of course, you know this is going to do remainder of 0, 0, 0, 1, 0, 0. So in this case, we're going to have like true, you know, true, 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 false, true, true. Now with this list comprehension, this effectively goes through and generates all of these before realizing, hang on, I know this is false, but I've still taken the time to generate this here. So it's almost like, you know, if you can envision it this way, if we were going from left to right, you'd say, yep, 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 false. Okay, we should probably stop here. But because this is a list comprehension, it generates the last 2 anyway. And, you know, imagine if this went on for like for years down here. We're generating all of these pointless things when we could have just stopped here. So make this a generator expression instead. You get the same result. However, you know, this is going to be yielding those things. It's going to yield this, 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 this comes out as false. So therefore stop. That's it, right? So that's, I know it's kind of a more of a niche application. But yeah, it's something definitely worth bearing in mind. If anyone's ever used pylint, so you can use pylint to kind of go over your code. If you ever do anything like this with a list comprehension here, pylint actually has a point in the linter of shouting at you if you do this, which is kind of cool. It detects that you've passed a list comprehension, you know, went into this all function, where if this was a generator, it's potentially more efficient because if this is stopping early for whatever reason, it will actually finish early, whereas with a list comprehension, it will find the false and just keep on going all the way to the end. So just something to bear in mind. I get it, it's a fairly specific use case, but just to recap one more time, the main difference of your generator expression is that it generates these on the fly when they're asked for, unlike a list comprehension, which basically says generate everything at once and just occupy all that memory, even if they aren't being used straight away. But yeah, that's it, guys. If you can find time to use this new code, I'd highly recommend it, and really impressive to learn, and they're nice and efficient. But yeah, cheers for watching, guys, and see you all in the next video.